This lesson is about polynomial and rational inequalities. When solving linear inequalities, you basically use the same rules of solving equations in order to get your answers. The only additional rule you must consider is that when multiplying or dividing by a negative constant, the inequality symbol must be flipped. So for instance, in the equation, negative 3x plus 5 is greater than 7. I would start out solving this inequality by subtracting 5 from both sides. In the same way I would do if this was negative 3x plus 5 equals 7, if it was an equation. The 5 cancels, and I have negative 3x is greater than 2, because 7 minus 5 is 2. The only thing that I have to be careful of is in the next step, in order to get x by itself, I need to divide by the constant negative 3. But whenever you divide by a negative number, you have to remember to flip your inequality sign around. So the solution here is x is less than negative 2/3. Graphically, what that looks like is we have the point negative 2/3, and that's not part of the solution because this is x is less than negative 2/3. So I would shade to the left. And what that means is any value that I choose that is less than negative 2/3 would make this a true statement. Any value that I choose that's greater than negative 2/3 would make this an untrue statement. For instance, if I chose x equals negative 1, if I plug negative 1 into the original inequality, then I would have negative 3 times negative 1 plus 5 should be greater than 7. Negative 3 times negative 1 is positive 3. 3 plus 5 is 8, and 8 is greater than 7. So that results in a true statement. However, if I choose a value that's greater than negative 2/3, then let's say, for instance, 0. If I plug this into the original inequality, negative 3 times 0 plus 5 should be greater than 7. But negative 3 times 0 is 0, plus 5 is just 5. But that's not greater than 7. That's an untrue statement. So any number for x that I choose that is greater than or equal to negative 2/3 would lead to an untrue statement. Any value that I chose that's less than negative 2/3 would lead to a true statement. Oftentimes, you're required to answer your final solution in what's referred to as interval notation. Interval notation in this case would look like all the values from negative infinity up to negative 2/3, and I'm using a parentheses around the negative 2/3 because it's not included in the final set. When working with quadratic or polynomial inequalities, you must rely on the use of sign charts. This is because when you multiply two factors together, the sign of the final answer is only dependent on whether the signs of the original factors are the same or are different. So let's take a look at some examples. Suppose I have the inequality x squared minus x minus 12 is less than 0. In order to solve this, what I need to do is factor this polynomial. And since it's a quadratic, it would factor into two terms, x and x. It looks like 3 and 4 are good possibilities for factors. If the 3 is positive and the 4 is negative, that should work out. Now, The issue here in determining where this statement is positive and where it's negative. I have two numbers. One number is coming from the factor x plus 3. The other number is coming from the factor x minus 4. And the result of these numbers being less than 0, equal to 0, or greater than 0 are only dependent upon the signs of these two numbers. So for instance, if x was equal to 5, then 5 plus 3 would result in 8. 5 minus 4 would result in 1. 8 times 1 is a positive number. So a positive times a positive is positive. However, if I chose a different value for x, if I chose 2, 2 plus 3 is 5. 2 minus 4 is negative 2. 5 times negative 2 is negative 10. So we have a negative result. So whether or not the final answer is positive or negative really only relies on the signs of these two factors once you plug a number in for x, which makes it kind of difficult to continue solving the way that we have. A lot of students would like to try to take the individual factors and set them less than 0 and solve that way. That will lead to incorrect answers. So what you need to do is use a sign chart. So on your sign chart, you want to place your factors. So negative 3 is a factor, and 4 is a factor. Notice these are the values that you get when you set each of the factor x plus 3 equal to 0. So negative 3 is the 0. So put your zeros on the sign chart is what I should say properly. Now, the result being positive or negative really only depends on whether the numbers are above the x-axis or below the x-axis. So we just need to choose a test value in each of these intervals and see on individual intervals if the result is positive or negative. So for instance, if I chose a test value of x equals negative 4, which is on my first interval, then when I take negative 4 and place it into my factored polynomial, it's negative 4 plus 3, because that first factor was x plus 3. The next factor is negative 4 minus 4, because that factor was x minus 4, and I've just plugged in x. Negative 4 plus 3 is negative 1. Negative 4 minus 4 is negative 8. So I have a negative number times a negative number. When you multiply a negative times a negative, the result is positive. This number in particular is positive 8. But we're not so interested in what the value of the number is, just what the sign of the number is. Because if one number on this interval is positive, then all numbers in that interval is positive. Next, I'll choose 0. If I plug 0 in, then the factor x plus 3 is 0 plus 3, and the factor 0 minus 4, I end up with 3 times negative 4. The result of which is negative 12, but again, it only matters that it's a negative number. So everything on that interval is going to be negative or below the x-axis. All right, the last interval, I'll pick a value that's between 4 and infinity. So how about 5? So when x equals 5, my factors become 5 plus 3 times 5 minus 4. This would be 8 times 1, and the result is positive, which means everything on this last interval is going to be positive. Now, the original question wanted to know, when is this polynomial x squared minus x minus 12 less than 0? Well, it's less than 0 when it is negative. And it's going to be negative on the interval from -3 to +4, because I've determined through my sign chart that everything on that interval is negative. And I'm using the parentheses here because I'm not including, since this is just less than 0 and not less than or equal to 0. So my solution from my sign chart is -3 to +4, that interval right there. I'd like to show you a graph of this so you can further understand how this is working. So let's do a quick sketch of this graph. X squared minus x minus 12 is a polynomial, and the zeros of this polynomial are at -3 and +4. Now, I'm not going to be terribly accurate with the rest of my polynomial. I do know, in fact, that the polynomial has a y-intercept of -12, but -12 doesn't appear on my chart, so I'm just going to sketch from here forward. The thing about this is, because the leading term coefficient of this polynomial is positive, this parabola would open upward. So my parabola would look something like this when I sketch it. And from that, what I can deduce is everything on the interval from here down to this point is positive. That's all above the x-axis. So on this interval from here back to -infinity, the graph is entirely positive. That's what we determined from our sign chart. Similarly, on this side, everything along here is above the x-axis. So on that interval, from 4 to +infinity, that is positive. And going from this point all the way along to this point, everything is below the x-axis, so we're entirely negative on this interval, which is what we saw from our sign chart. So our sign chart basically is showing us simply where our function, the graph of our function, would be positive or negative. The only place that we can change from positive to negative is at a 0 or a point that's undefined. For polynomials, all you have to worry about are zeros. Let's take a look at another example. 2x squared minus x is greater than or equal to 6. Now there's going to be a little bit more work ahead of time here. And one thing that I will mention is that it's going to be much easier to determine where a function is greater than 0, less than 0, rather than greater than 6 or less than 6. So in these problems, I'm always going to bring all my terms to one side of the equation. So 2x squared minus x minus 6 is greater than or equal to 0. That's going to be my starting point. The next thing that I'm going to do, because I now have a quadratic, is factor this polynomial. The leading term coefficient is not equal to 1, which means factoring gets a little bit more complex. But let's give it a shot here. So 2x and x are the only things that would multiply together to result in 2x squared. So I'm certain that the first terms are this. The other terms in these polynomials, the factors, are very likely going to be either 2 and 3 or 1 and 6. Let's try 2 and 3 first. So one thing that I would like to mention about this is when I choose 2 and 3, if you'll notice in the first factor, I would have a common factor of 2. If there wasn't a common factor of 2 in the original polynomial altogether, then there's not going to be one in any of the individual factors. So I'm already certain that that's not the factors. So 3 and 2 is what I'll try first. Now, this would multiply into 3x, and these would multiply to 4x, which I could get to add to negative x if I had negative 4x and positive 3x. So I would need a negative on this 2 and a positive on this 3. So that looks like my correct factorization. Now that I have it factored, I can create a sign chart. And on my sign chart, all I need to place are the zeros. So my zeros are positive 2. That's an easy one to see. And the other one, you may have to take a second to set it equal to 0 and solve. So if you took 2x plus 3 and set it equal to 0, then you can change that factor into a 0, which would be negative 3/2 in this case. Now, the next thing that I need to do is determine where this function is positive and where it's negative. And you can go through and you can do a test value for each and every interval. But what we've learned in the past about multiplicity can really simplify our process on this sign chart. So for instance, both of these zeros, the negative 3/2 and the 2, are multiplicity 1, which is an odd multiplicity, meaning that you would change signs over that value. So for instance, if I determine one interval, if it's positive or negative, I can use multiplicity to determine the rest of the intervals. The easiest one would involve 0. So if I put 0 in, then it would be 2 times 0 plus 3, which is 3, and 0 minus 2, which is negative 2. 3 times negative 2 results in a negative number. Now, because the multiplicity of the 0, 2 is odd, that means I would change signs going across that 0. And similarly, the multiplicity of the negative 3/2 is odd, so I would change signs there as well. If you're uncomfortable with determining that, you can always choose more test values and see for yourself. So for instance, a value that's less than negative 3/2 would be negative 2. You could plug negative 2 into your polynomial and see if it's positive or negative. A value that is greater than 2 would be 3. You could plug 3 in and see if it's positive or negative. That would always work. But using the argument of multiplicity can save you a lot of time. So we're looking to where this polynomial is greater than or equal to 0. So that's going to be where it's positive. Since it's greater than or equal to, I would use solid circles. And it's positive on this interval, and it's positive on this interval. So my solution is the interval from negative infinity up to negative 3/2 inclusive, and then starting from positive 2 going to positive infinity inclusive. And remember the u standing for the operation union takes two sets and joins them together into one single set. So that's how we express a compound set. Here's one more example using a polynomial inequality. Now, if you'll notice, the polynomial here is already factored. It is not a quadratic, which would make it much more difficult to factor if we weren't given the polynomial in factored form already. So, since it's in factored form, we can already identify the zeros. And those zeros are -1, -4. Let me change this one around then. All right, -4, -1, and +2. Oops. So, those are my zeros. But one thing you want to make sure you notice is that -4 is a zero of multiplicity 2. And I know that because of the square on that particular zero. So I would, on both sides of that zero, I would always stay the same sign. Now, in order to solve this, I need to determine where my function is positive and where it is negative. So I'm just going to choose one interval and use that value to test. So x equals 0 is always the easiest if it's not already a 0. So I would have -2 times 4 squared times 1. The result of this is going to be a negative number. So everything on this interval is going to be negative. Now the 0, 2, this number right here, the 0, it is a 0 of multiplicity 1, which means I would change signs across that 0. Same thing here. -1 is multiplicity 1, so I would change signs again. But -4 is multiplicity 2, and since that's even multiplicity, I stay the same sign over it. Now I'm looking for where this is greater than or equal to 0. So it looks like I'm greater than or equal to 0 on this interval, including the -4, on this interval, including the -1. I skip the next interval, but I include the 2, and then go to positive infinity. So it looks like my solution can be expressed as the interval from -infinity up to -1 inclusive. Since I have all the values, including that -4 before and after it, I can go ahead and just include that as one set. And then from 2 off to positive infinity. Let's say we have the same problem, but instead we want to do only where this is greater than 0. So I'm going to just copy the same sign chart down. So -4, -1, and 2. And we had positive, positive, negative, and positive. Now, if I only want to know where this is greater than 0, the situation only changes a little bit. So it would be on this interval, but not including the -4. Then on this interval, not including the -1. And then not including the 2, but on this next interval here. So now my solution would look a little bit different. So that those first two sets can't really fuse together because the -4 is not included. So my solution would now look like the interval from -infinity to -4, then from -4 up to -1, and then from 2 to positive infinity. And that would be the solution in interval notation. Rational inequalities behave in the same way as polynomial inequalities, but you must also consider the location of vertical asymptotes in addition to x-intercepts as places where the graph changes signs. And you also must make sure you know that you cannot include a vertical asymptote as part of your solution. Let's look at an example. X plus 2 divided by the quantities x plus 5 times x minus 1 squared is less than or equal to 0. So I want to create a sign chart, and this is already in factored form. I don't need to do any work. If it wasn't in factored form, I would need to express it in factored form. And also, if there was anything on the right-hand side of the equation, if it wasn't just 0, I would need to move that term over, combine like terms, and get it in this form. But already being in this form is handy. So the zeros and asymptotes. I have a 0 at -2, and I have an asymptote at -5, and I'm going to mark that as an asymptote. And I also have an asymptote at +1. The reason I'm marking those as vertical asymptotes is because no matter what, I cannot include those two values as part of my solution. So I'm going to go ahead and right now put them as open circles, just to remind myself that no matter what I do, that can't be part of my solution. So the next thing that I need to do is determine where this function is positive and where it's negative. So if you'll notice, the -2 and -5 are multiplicity 1, but this 1 is multiplicity 2. So I'm going to take 0 and plug that in and see what I end up with. So when x is equal to 0, I would have 2 over 5 times -1 squared. -1 squared would be +1. The rest of these numbers are positive, so the result of all that is on this interval, I would result with a positive values. And since my vertical asymptote is multiplicity 2, all the values in this interval would also be positive. I stay the same sign across something that is a 0 or an asymptote that is even multiplicity. Going the other direction, -2 is a 0 that is odd multiplicity. It's multiplicity 1. So I change sign. -5 is a 0, well, an asymptote, but you can think of it as a 0. They behave in the same way. Multiplicity 1. So again, I change signs. Now, the answer is looking for where this is less than or equal to 0. So it's less than or equal to 0 on the interval right along here. But be careful in that you can include the -2, because it's less than or equal to. You can include the -2, but you still can't include the -5 because it's an asymptote, and that could never be part of a solution. So your final answer here, your solution, is going to be the interval from -5, not including the -5, up to -2 inclusive.